All right, hello everyone. Hello Ariel, John, Kelby, and Shyam. Thank you for attending this live lecture. So as you know, like the first bunch of lectures we had were pre-recorded. This is an attempt at interjecting a bunch of live lectures, and who knows, perhaps we might do it all live until the end of the semester. Depends on how it goes and how much technical difficulties we face. So having said that, I want to thank everyone for attending, and hopefully this goes well. All right, so today the topic we're going to cover is going to be sinusoidal forcing, sinusoidal and complex forcing functions and their response. So up to this point, what did we cover up to this point? We covered. Let me just do a sort of a quick review. We covered complex numbers, right, and their representation and how to deal with them. And then we talked about first order and second order transients, right? And those transients were mainly dealing with circuits where we have DC forcing functions, mainly meaning that the sources in the circuit, so whatever block or box represents a circuit, this could be any circuit, right? The forcing functions, meaning the sources that drive the circuit, are all DC, meaning if you plot them with respect to time, they're fixed, right? But transients are injected by doing something with the circuit that suddenly steps it from one mode to another. So you could either flip a switch, or you can have a voltage source that pulses. For example, it could step, the voltage source could step, or it could pulse, or it could do something like this. It could go through multiple steps, right? But ultimately, in every interval where we're studying the transient, that source is fixed as DC, right? As we transition into this course, we kind of slowly move away from that, and we want to go to a place where we can handle any general signal, general forcing function, right? We will get there once we study the Laplace transform, but intermediate step that we're going to go through, and a very important actually intermediate step, which is the step of doing AC analysis. And that's very important because the bulk of the electrical phenomena that we deal with is AC in nature. If you examine the outlet, your outlet, or the power transmission and distribution system, it's all AC based. It's all sinusoidal generation of voltages and currents, right? And we kind of introduced the sinusoidal function last time, right? And talked a bit about mathematically representing it. And we talked about what it means to have sinusoids that are in phase, out of phase, so on and so forth. So we dealt with all this verbiage, okay? So now we want to deal, after we introduce sinusoidal functions mathematically, we want to deal now with the sinusoidal function as a forcing function, as an input that you apply to a circuit, right? So you have a circuit representing it as a box, and you apply a sinusoidal input to that circuit, let's say a voltage. It could be a current, it doesn't have to be a voltage. And then you get some response within the circuit. The circuit responds to this voltage. Let's say a certain branch has a certain current through it, right? The idea is that this response is going to have a transient, meaning the moment I apply this voltage, and this voltage, let's say, is some magnitude, it's a sinusoid. That's what we are constraining ourselves to, sinusoidal forcing functions. So it has some magnitude, it's a sine function, it has some frequency, it has some phase angle, right? The moment I introduce this forcing function, the circuit is going to go through a transient. And then after it goes through the transient, after it finishes the transient, it will settle at steady state. Right? We don't have the tools yet to understand what the transient looks like. If it was a DC forcing function, yeah, we can say what the transient looks like, but we don't have that yet, and we will ignore the transient for now, right? But what we definitely have the tools to study is the steady state. We definitely can study the steady state. What happens after the circuit settles down and all the transients die away, right? And remember, look back at when we discussed solutions to differential equations, we said any general differential equation will have, let's say A, B, will have, and we have a forcing function, ft. It will have a homogeneous solution, meaning the solution of the equation when the forcing function is 0. That's called the natural response. Plus, it's going to have a particular response, right? And we said the technique that we use is that the particular response will mainly follow the form of the forcing function. Okay? So in this case, we can claim that the steady state response, we still don't know what it is, but at least it will follow the form of the forcing function, right? If you're swinging, if you have a kid and you're swinging them, your forcing function is the force you apply on the swing, and you're swinging back and forth. The kid will not go in circles or not, it will follow your forcing function, right? So the idea here is that the response is going to follow the forcing function. So the response is going to look like a sinusoid. It's going to have some magnitude, let's say B, and then some frequency. It will have the same frequency, and it will have another phase, right? The idea is that can we deduce what the response is from the forcing function just by solving the differential equation? Yes, we can. We will discover that, yes, we can do that, but then we will discover something further. We can actually simplify the analysis by introducing some new concepts, right? And those new concepts will be the concepts of frequency domain analysis. And then we'll introduce the concept of a phasor, right? And we will discuss that later as we move on in this chapter. All right. So let's do an example. Let's show how can, based on this basic assumption that we've used before, that the steady state response is going to match the forcing function, can we deduce just from inspection, just from looking at the differential equation, what the steady state response is? Let's take a simple example. So we start with a simple example, not a very complicated circuit, just voltage source, resistor, inductor, and then we have the current, and then the forcing function V of t is just Vm cosine omega t. You could do sine or cosine. Typically, we prefer to use cosine, but you can do sine or cosine, doesn't matter. So we can get the differential equation using KVL. Differential equation is simply L di by dt plus Ri equals Vm cosine omega t. This is V of t. Right? And we said that the response is gonna be something that matches the forcing function. So let's write the response in general. The response in general is going to be some magnitude, a cosine function, omega t, and it could be it could have some phase. It doesn't have to match it exactly. It only matches it in form. It's some kind of cosine with a certain magnitude and phase. Using this differential equation, now we want to see if we can solve for A and phi. Because once we solve for A and phi, we have identified the response completely. All right. Before doing that, let me write IT in a different form. Let me expand this. Let me use the summation identity. So alpha plus beta, right? We remember that identity. So if I use that identity, I get A cosine phi, cosine omega t minus A sine phi sine omega t. Okay. It's clear that A cosine phi is constant and A sine phi is constant. So let's define new constants, A1 and A2, to represent those two constants. Right. So I of t is going to be just A1 cosine omega t plus A2 sine omega t. All I did is renamed constants. That's all. A1 is going to be A cosine phi, and A2 is going to be, oh, minus sign, sorry. Okay, it's going to be, no, plus, sorry. Okay, the minus goes into the definition. So A2 is going to be minus A sine phi. Okay, let's differentiate this. Simple, it's going to be minus A1 omega sine omega t. That's how we differentiate cosine. And then plus A2 omega cosine omega t. Right? All that is left now is plugging this and this into the differential equation. Right? So L di by dt is going to be, I just take this expression, multiply it by L. So I'm going to have minus A1 omega L sine omega t plus A2 omega L cosine omega t. That's L di by dt. And then IT is going to be plus A1 cosine omega t plus A2 sine omega t. R. Okay, remember the differential equation has R in it multiplied by I. So there's an R here and an R here. This equals the source, Vm cosine omega t. All we have to do now is equate. So we have the cosines and then we have the sines. The terms, the coefficients of the cosines should be equal on the right-hand side and the left-hand side. So we end up with the expression that, where is it? Oh yeah, so cosine we have RA1 plus this term now, A2 omega L equals Vm. Let's call this equation 2. Equation 1 is going to be the sine coefficients, going to be minus A1 omega L plus RA2 equals 0, because there's no sign on the right-hand side. Right, two equations, two unknowns, and we can use those two equations to solve for A1 and A2. So let's take one. From one, I can say that A2 equals A1 omega L over R. Substitute that in 2. I end up with what? Where is 2? Oh, this is 2. Okay, so so RA1 plus omega squared L squared over R, right? A1 equals Vm. This is the equation. Just multiply by R on all sides. So I end up with R squared. Take everything out. So R squared, rearrange stuff. I end up with this expression equals RVM. So I've solved for A1. A1 is going to be RVM over R squared plus omega squared L squared. And what is A2? A2 is just simply omega A1 times omega L over R. So A2 is going to be omega L Vm over R squared plus omega squared L squared. So it's a bit of analysis, bit of manipulation. And as we could move forward into this chapter, the point is that to find techniques, define mathematical objects that can reduce the requirement of doing all this stuff. Okay. But we've at this point we've solved for A1 and A2, and that means we solved for I of t. I of t equals, I can just plug in A1 and A2, right? RVM over R squared plus omega squared L squared cosine omega t plus A2, which is omega L Vm over R squared plus omega squared L squared sine omega t. Okay. Everyone following up to this point? Okay. I just want to check that there is responsiveness, that I haven't accidentally forced everyone on mute or something like that. Okay. Okay. So I'm going to assume things are good. If there are any technical difficulties, you can let me know later too. Okay. So I want to write this in this form, right? I want to write this as A cosine omega t plus phi. So I've solved for I of t, right? Right. That's easy, right? So what is A1? A1 is A cosine phi, right? And A2, I think we did that up here. Yeah, A2 is minus A sine phi. So I want to solve for A and phi. Well, let's solve for phi first. I can take A2 minus A2 over A1. What's that? That's going to be A sine phi over A cosine phi. That's going to be tan phi. So that's it. Phi equals tan inverse minus A2 over A1. This is A2 and this is A1. So it's going to be, the denominator is going to cancel. It's going to be minus omega L Vm over R Vm. Vm cancels. I end up with minus omega L over R. That's phi. That's the phase angle, right? And then what about A? How do I find A? Well, A1 squared plus A2 squared equals A squared cosine phi plus A squared sine squared phi. And we know that cosine squared plus sine squared is 1. That's a basic identity, right? So A is going to be square root of A1 squared plus A2 squared, right? That's what it's going to be. So I need to take A1 and square it. I end up with R squared Vm squared over, I guess, R squared plus omega squared L squared. The whole thing squared, a lot of squaring going on. And then, yeah, this plus omega squared L squared Vm squared over R squared plus omega squared L squared squared, right? I can, this is A, square root of that, right? So if I take Vm out, I have Vm. I end up with R squared plus omega squared L squared over R squared plus omega squared L squared squared, right? Right, I end up with 1 over square root R squared plus omega squared L squared. You see that, right? So I have, in the numerator, I have R squared plus omega squared L squared. And in the denominator, I have the same thing squared. So those cancels out. And there's a square root. So I end up with this expression for A. Right? Now we're ready to write the response in the standard form. Remember, this is the response due to the forced voltage source, forcing function applied to the circuit. It's going to look like this. It's going to be the magnitude of the forcing function over r squared plus omega squared L squared cosine omega t minus phi, plus phi, sorry. Phi is minus tan inverse omega L over R. Right? Notice that what makes the response in phase with the forcing function? Well, if L equals 0, the response will be in phase because the phase angle is going to be 0. What happens if R equals 0? If R equals 0, this will be infinity, right? This term is going to approach infinity. The what angle has a tangent of infinity? 90 degrees, right? So the phase angle is going to be minus 90 degrees. Okay, so the current, we say that the current lags the voltage by 90 degrees. It's behind the voltage by 90 degrees. Okay, this is a pretty simple circuit. So this is just a series connected R and L, and it required all this analysis, right, to kind of like find what the steady state response is going to be. Imagine if it was a more complicated circuit. So this kind of thing drove people into figuring out how do I simplify the process of solving those kind of AC circuits. There has to be a way of recognizing results that you're going to get all the time and kind of like abstracting them out and devising a process where we're analyzing those kind of circuits does not require this kind of analysis anymore. Yes, go ahead.
Yeah. What was the conclusion again? The current is lagging or the current is leading?
The current lags the voltage by 90 degrees.
Okay.
Right? Because why do we say lag? Because we say that this is the voltage, right? Let's say it's everything is cosine. Let's do it cosine. So this is the voltage V. The current has a phase angle of minus 90. So it has like omega t. The current is some Im cosine omega t minus 90 degrees. What does that mean? That means that minus 90 at angle minus 90, this angle at t equals 0, the cosine starts at minus 90. So the current looks something like this. So notice the voltage is happening first, and then the current is coming after. So that's why we say the current is lagging the voltage. It's coming after the voltage. And we can see it from the minus sign. If it was positive, we would say that the current was leading the voltage. Yes, go ahead. You were saying something, right?
Oh, no. I say I understand. Thank you.
All right, cool. All right. All right, so that's the response. And we want to now see if we can simplify the process of getting this response. And we want to ultimately be able to get response easily to any circuit, no matter how complex it is or how involved it is. We don't want to do this for circuits that have multiple elements and multiple nodes and meshes and so on and so forth. Okay, to get us there, one of the first steps we want to do is we want to move from the concept of a sinusoidal forcing function. We want to move away from this towards something more general. We want to move towards what's called a complex forcing function. And the key benefit of doing this is that when we are solving differential equation, this will, if we move from a sinusoidal forcing function in AC analysis to a complex forcing function, this will lead to algebraic equations when solving a network. Meaning that instead of getting and trying to solve differential equations, if we stick with complex forcing functions to represent our forcing functions, we will end up reducing the problem to just solving algebraic equations. Why is that good? Because remember, in networks 1, all your analysis is based on Ohm's law, V equals Ri, right? And then you use nodal and mesh and other techniques. And the point is, ultimately, you get a bunch of algebraic equations that you solve. Right? The problem when we move to the transient analysis and steady state analysis with other kind of forcing functions other than DC is that we don't get algebraic equations anymore. We get differential equations, which are harder to solve than algebraic equations, right? But when we use the techniques that are gonna start to implement by imposing a complex forcing function, we will get to that point again where we reduce differential equations back into algebraic equations and solve them just in this exactly the same way we solve the algebraic equations in network 1, right? So that's our goal. That's where we're aiming at, okay? So what's the complex forcing function? Complex forcing function is that simple. Instead of saying V of t equals some magnitude and some cosine, we say that V of t is equal to it's some complex function in the exponential form. Let's use the exponential form, right? It's something like this. It's Vm ej omega t. And using Euler's formula, this is just equivalent to Vm cosine omega t plus j Vm sine omega t. That's what it is. It's a function whose real part is a sinusoid in this form and whose imaginary part is a sinusoid, right? And we can apply it to circuits. So I can have my circuit. I apply this Vt, this complex function, this Vm ej omega t. I check a response in the circuit, right? And the response is going to be another complex function. It's going to be Im, it's going to be a complex response. It's going to be Im ej omega t plus some phase, right? Why can we do that? Why can we, I mean, we can do that, that's fine. Is the response still valid? Yeah, the response is still valid. If we want to find the response to Vm cosine omega t, which is a real life scenario, I mean, there's no complex signal in reality. We just take the real part of the response and we get the actual response to Vm cosine omega t. Why does that work? That works because circuits are linear. Meaning if I have a circuit and I give it Vm cosine omega t and it gives me a certain response, let's call it R1 of t, this is response 1, at steady state. This is all at steady state. And then I give it Vm sine omega t, and it gives me some response R2, right? If I multiply the property of any linear circuit, if I multiply the input by a certain quantity, like if I multiply this by 5, the output will be multiplied by 5. That's the basic property of linear circuits, right? It also follows that if I multiply the input by a complex constant, I multiply the output by the same complex constant. Linearity still applies even if the constant is complex, right? And then the other basic property of linear systems or linear circuits is if I add two inputs together, I get the sum of the responses. So the same circuit, this is circuit. If I sum those two inputs, I sum Vm cosine omega t plus j Vm sine omega t, I should get R1 of t plus j R2 of t. Okay, so just by solving the response of the circuit to Vm ej omega t, using solving the response due to the complex forcing function, the response that I get, whatever it is, let's say this is RT, R complex T, right? It's going to have already encoded in it the solution of due to the response due to the real part and the response due to the imaginary part. If I want to take the response, if I'm interested in the response due to the real part, which is what I'm interested in because all my real life signals are real, I just take the real part of it. Okay? So what I'm trying to say is that embedded within the complex response is the real response, right? Why do we want to do this complication? Why do we want to solve for complex forcing functions instead of just using the real function? It makes the solution easier. It makes getting or arriving at the solution easier. Okay, so let's just to show how it makes it easier. Let's redo the example. Let's redo our example. So I want to take this voltage source, and now I want to apply a complex forcing function, Vm ej omega t, whose real part is the real response, real forcing function I'm interested in solving the circuit for, right? Cosine omega t, Vm cosine omega t. I'm really interested in solving the circuit for Vm cosine omega t, but I want to now apply I want to take this as the real part of the complex forcing function, and then I want to solve for this, right? So this makes now solving the problem easier. I can just say that I of t, the response, is going to follow. This is the basic thing. The response is always going to follow the form of the forcing function. So the response is always going to be also another complex function, right? It's going to be Im ej omega t plus phi. Right? I plug it back into the differential equation, Ri plus L di by dt equals V of t. And now I don't have to do any of the cosine and sine differentiation and the constants A1 and A2 and all of that. I don't need to do that anymore. I just plug in. So I have R Im ej omega t. I'll use the exponential property and spread this out. So it's going to be ej omega t ej phi plus L. What happens when I differentiate this? This is an exponential function, right? I can differentiate it easily. This is going to be j omega L, and then just the exponential function. It's going to be ej omega t plus phi. So let me write it this way: ej omega t ej phi, right, equals Vm ej omega t. A curious thing happens. Notice that ej omega t is common. I can take it out. And I really need to solve only now one equation. I need only to solve R Im ej phi plus j omega L Im ej phi equals Vm. Right? I need to solve for Im. What do I need to solve? I need to solve for right? And I can solve for it, right? So the unknowns are Im and ej phi, right? I can take them out. So I end up with Im ej phi times what? Times R plus j omega L equals Vm, right? So Im, those are the two unknowns, the magnitude and the phase, just equals Vm over R plus j omega L. Right? And this is a complex number equals another complex number. One is in exponential form, the other is in rectangular form. I want to compare them, right? I want to find Im and phi. All I need to do is to convert this back into exponential, right? So how do I do that? Well, let's do that. Let's say Vm, and then I multiply by R minus j omega L over R minus j omega L times r plus j omega L. That gives me r squared plus omega squared L squared, right? I want to convert this now into this is still Im Ej phi. I want to convert this now into exponential form, so I need to find its magnitude, right? So I find its magnitude by taking r squared plus omega squared L squared square root over r squared plus omega squared L squared Vm. That's the magnitude. And what's the phase? The phase is going to be the imaginary part over the, I mean, the tangent of the phase is the imaginary part over the real part. So it's going to be the tan inverse minus tan inverse because of the minus sign. You can take the minus sign out of the tan inverse of omega L over R. I got the same result I got before from just doing complex manipulation of complex numbers, right? So I end up with Im Ej phi equals square root cancels with this. I end up with Vm over square root r squared plus omega squared L squared. Ej minus tan minus 1 omega L over R. Okay, so this is Im and this is phi, right? So this is the complex response to the complex forcing function. The actual real response is going to be the real part of Im Ej omega t plus phi. Remember, we have to plug in back the omega t, right? Because the response needs to match the forcing function, and the forcing function has omega t in it, right? And this is just inspecting, right? This is going to be just Im. And then the real part is going to be cosine of this thing. And I ignore the imaginary part. So it's going to be cosine omega t minus tan inverse omega L over R. So I got the same response, and I seem to have gotten it in an easier manner, but just by doing complex number manipulations. Okay. So all of this suggests that there's a novel concept that we can introduce. The question is, why did complex analysis or complex manipulation or manipulating with complex numbers make things easier? There's something here we can abstract out, and some concept we can define, and that concept is called the concept of a phasor. And phasors are crucial in AC analysis, particularly in steady state AC analysis. Okay. So what's the concept of a phasor? Let's define a phasor. So V of t, let's say we have some forcing function, Vm Ej omega t. And we said it leads to some response, I of t. The response could be some voltage somewhere, some other voltage, doesn't have to be current. But I mean, the distinction is that this is the forcing function, and this is the source essentially, and this is the response. The response is going to look something like this: some magnitude, and then Ej omega t plus phi. Okay, we found, I mean, in the previous example, we found that, hey, when we plug this in into the differential equations, it turns out that Ej omega t was a common factor that we could have, but that we were easily able to cancel out from both sides, right, of the equation. It didn't factor in the solution anymore. And we find that this happens all the time. Ej omega t always turns out to be a common factor that you can just take out, and you're just, all that you need to solve for is the magnitude and the phase, right? So here's where the concept of the phasor comes in. It's from the concept of just solving the magnitude and the phase. We can in the equations that we're dealing with, we can always drop Ej omega t, right? Although we're dropping it from the expression, we know that it's always implicitly there. It's always implicitly there. We know it's there, but we don't have to worry about it. We just drop it out, right? So because we don't have to worry about it, we can express VM as like VM as follows, and IM the response as follows, IM EJ phi, right? So those are two complex numbers, right? So those are the phasor form of the voltage and the current. Just the magnitude here. This is EJ equivalent to EJ 0. 0 is 1, right? And then the current is IM EJ phi. So the representation of the responses and the forcing functions by just using their magnitudes and phases and representing them as complex numbers, right, is the phasor form. So those are phasors. And we can either use the exponential form to represent phasors. That's what phasors are, by the way. They are complex numbers. They are complex representations or complex numbers representing responses or forcing functions that are sinusoids. And we can either represent them in polar form, like I've done here, or more commonly in circuits and power systems, they represent them in polar form. So another way of representing those phasors is as follows: VM and IM angle phi, right? So those are also the phasor, the phasor representations. How do you get back from the phasor representation of a response or a forcing function to the real time, to the real representation? Well, let's say from VM I want to get the real representation. I just take the real part, I take VM, I always put back in the implicit EJ omega t that I removed, and then I take the real part, right? So this becomes VM cosine omega t. Same thing for IM. When I want to get back to the real representation, what the signal is really on the real line, which is the actual signal. There are no complex signals in reality, right? I take IM phi, I add in the implicit EJ omega t that I removed, and then I take the real part of it, right? So this will be just IM is the real part, and then I have this is equivalent to EJ phi, right? So I end up with EJ omega t plus phi. So I end up with cosine omega t plus phi. Okay. So this complex number representation of those forcing functions and responses is what's called a phasor, right? And it's a complex number. So the phasor is any complex number. It's any point on the complex plane. And any point on the complex plane can also be represented by an arrow, right, pointing to that number. So it's most common to see phasors represented as vectors, as arrows in the complex plane. That's why when I'm doing this on my notes, when I talk about phasors, I'm going to use this notation. I'm going to say V as a phasor, I'm going to use the arrow. If you're in a printed medium like a textbook or any book, or you're writing a paper, you would present phasors as boldface. So it would be some capital letter, boldface letter to represent a phasor. But since I cannot do boldface in my notes, I'll just use an arrow to kind of represent the vector nature of phasors, right? And in many ways, they do have a vector nature, right? Complex numbers do have a vectorial nature, right? Adding two complex numbers is similar to adding two vectors, right? If I sum two complex numbers, it's similar to adding two vectors. Okay. So this is the phasor representation. V is just VM, some phase, theta V, and I is just some magnitude, and some phase, let's say theta I, the phase of the current. Right? So this is like common practice. Right? it's okay to represent phasors this way. I will sometimes represent them this way. It's the same thing. Remember when we talked about different representations of complex numbers? That's all this is. A different representation of complex numbers. This is polar. This is exponential. Right? That's the most important fact, is that a phasor is a complex number. That's what you need to, right? When we introduce phasors to any circuit problem, what will happen is that instead of getting differential equations, everything is going to be reduced to algebraic equations, and we can use the same techniques that we used in circuits 1 to analyze those circuits. Okay, so I want to go back now to that example that we solved. I want to do it now in phasor notation, just to show you how to do it in phasor notation. So again, we have a voltage. Now I'm going to use phasor notation. So I have Vm, 0 degrees. I'm representing the voltage in phasor notation. Remember, there's an implicit ej omega t that I'm not writing. Right? And then I have the resistor, I have I, and then I have the inductor, L, right? I am going to solve I as a phasor. So this is V as a phasor, and then I'm solving I as a phasor, which is Im theta I. Okay, so again, let's go to the differential equation. LdI by dt plus Ri equals, I have a complex forcing function, so I have Vm 0 degrees. Let me put back the ej omega t, because we need it, because we're gonna differentiate here, right? It's gonna cancel out anyway, right? So L d Im theta I, that's the phasor representation of I. I put back the implicit ej omega t. Remember, ej omega t always exists. I just remove it because I know that it doesn't matter. It's always there, right? But to differentiate, I need to put it in so that I can do the differentiation. Plus R Im theta I ej omega t equals Vm 0 degrees ej omega t. So I do the differentiation. I end up with actually, let me write it as a phasor. So let me just write I phasor, I phasor. So this is the phasor with an implicit ej omega t added back. This is V phasor, right? And I just differentiate. I end up with j omega L I phasor ej omega t plus R I phasor ej omega t equals V phasor ej omega t. And as usual, ej omega t is common and cancels out. I end up with one equation I need to solve. So it's going to be I phasor times R plus j omega L equals V phasor. So I phasor is going to be V phasor over R plus j omega L. That's how we solve the equation in phasor form. This phasor is just going to have a magnitude and an angle. Let's call it phi. Right, and as usual, this is I can solve this, right? So this is, I can find the magnitude of this. So this will be the magnitude of the phasor numerator over the magnitude of the denominator. You know, the magnitude of two complex numbers like this is going to be just the magnitude of the numerator over the magnitude of the denominator, right? And then the angle is just going to be, this is in the denominator, so it's going to be minus sign the angle of this complex number, which is going to be tan inverse omega L over R. I get the same result, right? It's just I'm using phasor notation in this case. I of t is just going to be now the real part of this. The real part of this after I inject back ej omega t. So I inject back ej omega t, I take the real part of this, I end up with Vm over R squared plus omega squared L squared cosine omega t minus tan inverse omega L over I. Okay. All right. So this is like if you have any circuit, you would look at any source. If you have some magnitude and a cosine, you turn this into a phasor by just taking the magnitude and taking the angle of the cosine, right? If you have some sign somewhere, Vm sine omega t, we know that sine is 90 degrees away from cosine, so this is going to be just the angle plus 90 degrees. 90 degrees represents the sine. Okay. Right? Why? Because if I have cosine, let's say omega t minus 90 degrees, that's going to be cosine omega t or minus 90 degrees, sorry. That's going to be cosine omega t from the trigonometric identity, cosine 90, which is 1, plus sine omega t, sine 90, which is 1. Sorry, cosine 90 is 0, so this goes away. So cosine omega t minus 90 is equivalent to sine. If you have a problem where all of them are sines, that's fine. You don't have to shift the 90 degrees. You only have to do this shifting. I can always assume that the sine is the real part and j is the, no, sorry. I can always do the complex response, and then I can take the imaginary part to represent my real response. Okay? All right. Let's apply the phasor concept to the basic circuit elements. So we have the basic circuit elements, the R, C, and L. What happens if we apply the phasor concept to those elements? So we have to go back to the, so remember we said that the basic advantage of using a phasors or the phasor concept is that it reduces differential equations into algebraic equations. That means what that means is that it should reduce the relationship between the voltage and the current for the basic elements into something like Ohm's law. Because that's the only way you can get algebraic equations from circuits, right? So you have a big circuit, you apply the analysis techniques based on Ohm's law, and you get algebraic equations. If I'm claiming that the phasor concept gets me algebraic equations, that means that the phasor concept needs to reduce the VI relationships for R, C, and L to something that's kind of akin to Ohm's law, something where it's just current times a constant equals voltage, right? And this introduces the concept of impedance, which we will discuss next time, right? But let's first investigate the relationship between, as phasors, using the phasor concept, what is the relationship between the V phasor and the I phasor for an R, the V phasor and the I phasor for a C, and the V phasor and the I phasor for an L, right? For an R, it's simple, right? It's just V equals RI. I turn this into a phasor. Let's say I have a sinusoidal source. So I have the phi phasor. I have the implicit EJ omega t. RI phasor, right? EJ omega t, right? Cancel out. This is the basic relationship. V phasor equals RI phasor for a resistor. And the resistor is just a real number, right? The resistance is just a real number. So if I write it in the phasor in polar form, I have V theta V equals R I, the VM, sorry, IM theta I. This tells me that VM equals R IM. This is the relationship of the magnitudes, the same as Ohm's law. And this tells me that the angle of the voltage should be equal to the angle of the current. For a resistor, the voltage across the resistor and the current across the resistor should be in phase. They should be in phase from this equation, right? I'm equating this to this side, right? So those two complex numbers should be equal. This could only happen if the phase of V equals the phase of I. So if we draw it on the complex plane, let's say this is the arrow to the complex number representing V, and this is the arrow to the complex number represented I, right? They would be in phase. This kind of diagram, by the way, is called the phasor diagram, where we draw the arrows representing the signals in phasor form. Okay, so for the case of a resistor, the voltage across the resistor and the current through the resistor is in phase. What about the inductor for the L? Well, the basic equation in the time domain is as follows: L di by dt. Right? Let's write it in the frequency domain as phasors. So that tells me that V, I represent V as V ej omega t. I include the implicit ej omega t to do the derivation. And then L d over dt, instead of I put the phasor form, I phasor, and I include the implicit ej omega t. Remember, I is just Im theta I, and V is Vm theta V. Okay, I can differentiate this easily. I end up with V ej omega t equals j omega L. I differentiated the exponential. The phasor is constant. And then ej omega t. Again, ej omega t, as usual, cancels out. And I end up with this sort of weird different Ohm's law for the inductor. So this term here, j omega L, seems to be playing the role of a resistance for the inductor. It's just a constant, but now it's a complex constant instead of being a real constant. So this seems to be indicating that the inductor in the frequency domain is some kind of complex resistance, okay, where the resistance is a complex number. It's not actually called resistance, it will be called impedance, but we'll discuss that next lecture. Okay, but the point here is that I want to now check the magnitude and phase relationships between V and I for an inductor. So if I put in Vm theta V equals j omega L Im theta I, right? This is a complex number, this is a complex number I can compare, but I want to do something first. I want to represent J in its polar form. J in its polar form is just 1, 90 degrees. I can add it here, right? So I end up with just 1, and then theta I plus 90 degrees. Aha, so this tells me that Vm equals omega L Im. That's the relationship between the magnitude of the current and the voltage. But the angles now are not in phase. Theta V equals theta I plus 90 degrees, right? So going back to the complex plane, I have the arrow representing V, going to the complex number representing the phasor V. The angle of the current is going to be the same as the angle of the voltage minus 90 degrees. Right? So this is going to be I, is going to be lagging V by 90 degrees. So we say that for case of an inductor, the current through the inductor lags the voltage across the inductor by 90 degrees. And we discovered this lag simply by comparing the two phasors, right? And again, this is what's called a phasor diagram. All right. For C, let's do C quickly. C is just I equals C dV by dt. Phasor form is going to be I ej omega t equals C d over dt V ej omega t. Differentiation now is easy. I end up with j omega c ej of V EJ omega t. Again, EJ omega t. If you ever doing calculations and EJ omega t does not cancel out, you know that you have a problem, right? So I phasor equals J omega C V phasor. That tells me that Im theta I equals J omega C Vm theta V. So the magnitude of Im equals J omega C Vm. This suggests that this is some kind, oh, not J, just omega C. So this is something akin to Ohm's law. But then the phase now is I use the same trick. This is 190 degrees, right? So I end up with Im theta I equals omega C Vm theta V plus 90 degrees. So now in this case, if I have a certain V phasor, right? What would be theta I? Theta I equals theta V plus 90 degrees, right? So I is going to be leading the voltage. The phasor I is going to be leading the phasor V by 90 degrees. And we say for a capacitor, the current leads the voltage by 90 degrees. Okay, so this is kind of like our introduction to the concept of impedance, which we will discuss in detail in the next lecture. So kind of we're out of time. Let me see if I'm still. Okay, so thank you everyone for attending. If you have any questions, we can go through them now, or we can go through them through the discussion thread. I'm gonna see how well this recorded, and I'm gonna post it online, and we can take it from there. All right, thank you guys for attending this lecture. I'm gonna see you next time. I'm gonna stop sharing now.
Thank you.
Thank you.